Hello, this is the sixth in a series of screencasts on the subject of the chemistry of acids and bases for the module CHE10063. Okay, so today we're going to sort of finish our generalization of acids and base chemistry towards and talk about Lewis acids. Okay, the reading is essentially in inorganic chemistry, and the QR code that's on the slide in front of you links you directly to page 164, the title of which is Lewis acids, and it goes on from there basically. Okay, so what is a Lewis acid? Well, basically, we now have to move away from this Brownstead-Lowry definition of acidity via sort of just protons, okay? And now we start talking about electrons, okay? So a Lewis acid is defined as a species that will accept an electron pair, and a Lewis base is a species that donates one. Okay, so you effectively have Lewis acid is A and Lewis base is B with an electron pair explicitly written onto it. And the key point about this, as written on the slide, is that now we don't need protons to be involved in our reactions, and it allows for other types of reactions. Okay, so and those types can still involve protons, but we kind of look at them in a different way. So in the following example, we actually have a proton. It's a proton transfer reaction, but we can look at it from the perspective of Lewis acids. Okay, so essentially what we've got is we've got NH3, and this could take place in liquid NH3 or indeed in an aqueous condition, reacting with HCl. Okay, so HCl. And what we can do is we've got our Lewis base, which is our ammonia species, and we've got our Lewis acid, which is our HCl, which, of course, is also a Bronsted acid. And what happens is that the Lewis base donates a pair of electrons to the hydrogen, and that then breaks the bond in the HCl to form, a chloride species. Okay, so in this case, the HCl would obviously be a gas because it's bound. Yeah, so that would give us the following species. Okay, so you've got your NH4 plus and your Cl minus. Now, key point here is that the double-headed arrow, that indicates the movement of a pair of electrons, and you'll have more electron pair, and you'll have more about that as you talk more about organic chemistry this year and beyond. Okay, so you'll get used to the use of a double-headed arrow to indicate the movement of an electron pair. And the other key point is that this new species has a particular name. Okay, and we'll go into that on the next slide. But once again, you have your NH3 species is donating an electron pair, and the acid is taking that pair in, and what you're doing is you're forming this species at the end of it. Okay. Okay, so as I already said on the previous slide, we have a general way of writing these things with the Lewis acid being our species A and a Lewis base being our species B, with the electron pair clearly shown. Okay, and we have a fundamental reaction which is the same as the one I showed you on the previous slide, where you've got your acid reacting with your base, giving this species here, which is a complex adduct. And so I'm just going to write out another example of that, perhaps one that's a bit more obviously bonded at the end of it. So we've got a boron containing species here, and boron containing species are often Lewis acids, and I'll explain why that is on pretty much the next slide. And again, we're going to use the same base, which is our NH3. Yeah, NH3 has a nice electron pair, and what we do is we can draw our motion of our electron pair, and in this case it's going to go to the boron atom. Okay, so this is our Lewis acid, this is our Lewis base, and that is going to give us what we term as a complex adduct. So I'm going to draw this in. And you've got NH3 obviously. Now, strictly, the N then becomes positively charged and the boron becomes negatively charged. This species here is described as a complex adduct, as is written above. So this is like the classic Lewis base acid-base reaction. So there are several different types of Lewis acids. The first one, and probably the most common in many respects, are molecules that have an incomplete octet. So this includes the boron-containing species that I've already described. So boron-containing species, the boron has not got, it doesn't obey the rule of 8, and so we end up with essentially only 6 electrons around the boron atom, even in this molecule here. Okay, and what you have is you also have a vacant p orbital. So this is a vacant p orbital. And you'll do more about drawing orbitals with Dave when he talks about atomic orbitals in the near future. Okay, and of course, if you donate an electron pair into that vacant p orbital, then you complete the octet, and so therefore, the VS-EPR rules are more satisfied. So that's a favourable thing to do. Okay, so typically speaking, the types of elements that would include this would be the group 13 elements. So you've got things that include boron, things that include aluminium, and in every single case, they basically accept this electron pair into that p orbital. So the previous reaction we showed, where you have, essentially you've got your CH3 3b, and you've got your NH3, your ammonia reacting with that. You've got your acid, your base, and that gives us the complex adduct, which is the one I drew on the previous slide. Okay, which obviously the two things join together. Okay, so that's a fairly classic type of Lewis acid, and that's the way it reacts. But there are other different types of Lewis acid. Okay, so for example, you can see metal ions as being Lewis acids. Okay, so we've already met this kind of species and this kind of reaction because we already discussed aqua acids before. Okay, but when you put a Lewis acid, such as, in this case it's cobalt 2 plus, but it could be a bunch of different types of metal cations. If you dissolve that into water, then the water will surround that central metal cation in a way that is similar to what I've shown here. And in that case, you end up with a donation of the pair of electrons from the oxygen get donated to the metal to make the bonds that are shown. Okay, so then that again is where you have your metal behaving as a Lewis acid and your water behaving as a Lewis base. Another type of Lewis acid is a molecule or ion that has a complete octet already, but that can rearrange its bonds, its valence electrons, to accept something else. Okay, so one example of this would be CO2. You've got, your carbon has 2 double bonds around it, but we know that we can actually, with a carbon, for example, we can rearrange it so we can actually have 4 single bonds as well. And so what happens when you have carbon reacting with a hydroxyl group is you've got a movement of a pair of electrons into the carbon, and obviously we can't make a bond straight away because we can't form 5 bonds around the carbon, but we can break the double bond to the oxygen to form a single bond to the oxygen, and in doing so we again make our complex adduct with an O minus. Okay, so again we have an acid, a base, and a complex adduct. Now, one key point, and this again relates to the drawing of double-headed arrows, and you will hear this again in organic chemistry, is that they must always come from a lone pair. Okay, you're best off not doing it from a negative charge, because that's actually, a negative charge is only 1 electron. Okay, so the final type of Lewis acid is a molecular ion that can expand its valence shell. Okay, so a classic example of this is a species that is silicon based. Okay, so for example, I'm going to write out silicon tetrafluoride here. So what we've got is 4 fluorines around our silicon. Okay, and if you bring in 2 more fluoride anions, again, we can see the motion of a pair of electrons towards the silicon center, and we do that 2 times, and what happens is we get this species here. Okay, so we've got fluorine, 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 And of course, this one's going to have 6 fluorines around it. Yeah. Okay. And, it's obviously also 2 minus because it's had 2 negative charges added to it. Okay. And again, we've got our acid, our base times 2 basically, and complex adduct. Now, key point here would be that this species, this new species that's made, the complex adduct, in this silicon is hypervalent. Now, you're going to meet hypervalency in greater detail later on in the semester and next year. But basically, this is something that's common for halides of heavier p-block elements. So, for example, elements like silicon, arsenic, phosphorus. These are the sorts of things these are the sort of species that will show hypervalency. Okay. Okay, so let's talk about the relevance of this topic. Well, this topic is highly relevant to, commerce and to industry. For example, Lewis acid-base reactions are existing in, many processes that we see on a daily basis. For example, you've got cement mix in here. You've got the reason why carbon monoxide is toxic here. But equally, the same sort of thing applies to the way in which oxygen is carried around the body. And finally, there are many industrial processes such as this one. This is a Friedel-Crafts alkylation that you'll learn about, later in your studies at Kiel. But this one is one that is actually catalyzed by a Lewis acid. And so Lewis acid catalysis is a whole topic in its own right. So yeah, this is a highly relevant topic. So it might seem quite basic, but it does have significant industrial relevance. Okay, let's move on, and we're going to talk about some different types of Lewis acid reactions. Now, we've already seen one type. We've seen the complex formation. So this is where you have an acid plus a base giving us a complex adduct. And we've seen these, quite a lot of these examples, and that's what we've been doing for the past few slides. Okay, but there are other types of Lewis acid reactions. For example, we have a displacement reaction, and it's important to get the terminology right here. So this is a Lewis acid displacement reaction. It's where you've got a second base is coming in, reacting with a complex adduct that has already formed to give a new complex adduct and a new base. Okay, so you could just summarize it as complex adduct plus base 2 gives complex adduct, new complex adduct plus base 1. Okay, I'm going to write you an example here. So an example of this would be, for example, we've got a boron containing species. Again, boron containing species are kind of classic Lewis acid species, or Lewis acid base species. We often use these as examples. And in this case, we've got it. This is basically boron trifluoride dissolved in methyl ether. Okay. And when we bring in a stronger base, such as pyridine, which is this, and what happens is the pair of electrons goes there. We break this bond to reform our dimethyl ether, and we get a new complex adduct, which is sort of BF3 attached to the pyridine. Possibly one of the worst pyridines ever drawn, but nevertheless, you get the idea. And you get a regeneration of your dimethyl ether. Okay, so that's an example of a displacement reaction. Okay, and this often takes place with boron species, particularly because often sort of things like BF3, they're gases at room temperature. They tend to be dissolved in other species, other solvents such as ether or pyridine, in order for cancer. Another classic one they get dissolved in is THF, tetrahydrofuran. Okay. And sort of to put this into context, all of the Bronsted proton transfer reactions we've met so far are displacement reactions. Okay, and so for example, if you've got your acid, in this case nitric acid, right, reacting with water is in equilibrium, although obviously for nitric acid we could just use a straight arrow here with H3O plus AQ, or we've got to make our water liquid, plus NO3 minus. Okay, so that's our classic proton transfer equilibrium. Okay, what we have here is we have a base, which is our NO3 minus, being displaced by a stronger base with our H2O to give a new complex adduct, H3O plus the weaker base, NO3 minus. Okay. Right. The final note on Lewis acid reactions is a final type of Lewis acid base reactions, and this is a metathesis. Okay, so this is where you have complexes reacting together and we get an exchange within the complexes. So you can kind of see an example up here. You've got basically exchange of the bases, and one of the bases ends up attached to the other acid and the other base ends up attached to the first acid. So I might just use a different color to indicate where these go. Yeah, so it's just complete exchange, which is why it's called a metathesis, because metathesis is exchange. Okay, so an example of this, which I'll write out, is, and again, we're going to use a silicon containing species. Again, silicon containing species, quite common sort of Lewis acid species. Let's draw that out with some methyl groups. Okay, so we've got some methyl groups. Okay, and that's going to react with AgBr, so silver bromide. And what's going to happen is you're going to make, I'm just going to do it down here because I've got a bit more space that way. You're going to get a complete exchange. Okay, so we're going to have the bromine's going to come onto the silicon. Okay. Of course, the methyl groups remain in the same positions, but I'll draw them out anyway. And the iodine ends up on the silver, and I don't know why I drew it like that, but anyway, iodine ends up on the silver. Now, key point here with this reaction, I mean, this reaction obviously is going to be quite involved because you've got to break 2 bonds and remake 2 bonds. But in this case, what we're going to make is going to make silver iodide. And this is a precipitate. So this is actually the driving force for this reaction, is the precipitation of silver iodide. Okay, so the key point there is that this is going to be assisted by the formation of a second complex, which in this case is the silver iodide. Okay. And that's all for Lewis acid-base chemistry.